Welcome to lecture series on matrices. What you will learn in this lecture series are meaning of a matrix, some special matrices, operations on matrices, determinant of order 2 and order 3, inverse of a matrix, and systems of linear equations in matrix form. Lecture 1. Definition and some special matrices. A matrix is a rectangular or square array of numbers enclosed in bracket. The bracket is either of this type or this type. This is an example of a matrix. The dimension or order of a matrix is determined by the number of rows and columns in the matrix. For example, in the above matrix, this is row 1, this is row 2, this is row 3, this is column 1, this is column 2, this is column 3, and this is column 4. So the dimension of the above matrix is 3 by 4, written as this, 3 times 4. In general, an m by n matrix is the matrix having m rows and n columns. The entry in row I and column j of a matrix, say A, is usually written as this: A sub ij, where I represent the row and j represent the column. For example, in this matrix A, the entry A24, that is the element in row 2 column 4, is 6. That is, this is the element in row 2 column 4. The element in row 3 column 3 is 8. This is the element in row 3 column 3. And the element in row 1 column 2 is 1. This is the element in row 1 column 2, and so on. The general m by n matrix A can be written in full as follows: A equal to, the first row consists of the element A11, A12 to A1n. The second row consists of the element A21, A22 to A2n. If we continue, we will get to the last row, which consists of the element AM1, AM2 to AMN. This can also be written in a compact form as follows: A equals to, in bracket, A sub ij, for I going from 1 to m, and j from 1 to n. Transpose of a matrix. The transpose of a matrix A, designated A to power t or A prime, is a matrix obtained by interchanging the rows and columns of A. That is, row 1 of A is column 1 of A transpose, and vice versa. Row 2 of A is column 2 of A transpose, and vice versa, and so on. Thus, if A equals to, in bracket, Aij is an m by n matrix, then A transpose equals to, in bracket, Aj is an n by m matrix. Notice that the rows and column are interchanged in the A transpose, so j now come first before the I. Example 1. Consider the following 4 by 3 matrix A. Then this is the A transpose row 1 of A is now column 1 of A transpose. Row 2 is now column 2 here. Row 3 is now column 3. And row 4 is now column 4. Clearly we have 3 rows and 4 columns. So A transpose is a 3 by 4 matrix. Equality of matrices. Two matrices A and B are equal if and only if 1. Dimension of A is equal to dimension of B, and 2. Aij is equal to Bij. That's element in the same position are equal. Example 2. This matrix A is equal to this matrix B implies that A is equal to 3, B is equal to -2, C is equal to 0, and D is equal to 5. Trace of a matrix. The trace of a square matrix is the sum of the leading diagonal element. Note, the leading diagonal of a square matrix is the diagonal running from the top left corner to the bottom right corner. And the trace of a matrix A is abbreviated as this, TR of A. For an n by n matrix A, the trace of A is equal to the sum of AII as I goes from 1 to n. Please note, leading diagonal elements are denoted by AII. Example 3. Consider this 3 by 3 square matrix. Then the trace of A is the sum of the leading diagonal element 3 plus 4 plus 6, which is equal to 13. Now let us transpose this matrix A to obtain this. Also, the trace of A transpose is equal to 3 plus 4 plus 6, which is 13. So which therefore implies that transposing a matrix does not change the trace of that matrix. That's the trace of A transpose is equal to the trace of A. Some special matrices. The following special matrices shall be considered: square matrix, diagonal matrix, identity matrix, zero matrix, upper and lower triangular matrices, row and column matrices, symmetric and skew symmetric matrices, Hermitian and skew Hermitian matrices, unitary and orthogonal matrices. We begin with the square matrix. A matrix having the number of rows and columns equal is called a square matrix. This is an example of a 2 by 2 square matrix, while this is an example of a 3 by 3 square matrix. Principal diagonal. As defined earlier, the principal diagonal of a square matrix is the diagonal running from the top left corner to the bottom right corner of the matrix. That is, in an n by n square matrix A, the entries A11, A22, A33 to ANN constitute the leading diagonal element. Here is it. This diagonal is what we call the leading diagonal of a square matrix. diagonal stroke scalar matrix. A square matrix D is called a diagonal matrix if all its off-diagonal elements are zeros. An n by n diagonal matrix is written as follows: D equal to this. As you can see in this matrix, the off-diagonal elements are all zeros. We can also write it this way: D equals to diagonal in bracket D11, D222, DAN. Note, if the diagonal elements are all equal, the diagonal matrix becomes what we call a scalar matrix. Example 4. The matrix D equal to 6003 or D equals to diagonal 63 is a 2 by 2 diagonal matrix. Also, the matrix D equals to 500, 030, 001 or diagonal 531 is a 3 by 3 diagonal matrix. Identity matrix. An identity matrix is a diagonal matrix having only ones on the leading diagonal, or one can say an identity matrix is a scalar matrix with the diagonal element ones. The matrix denoted by I2 equals to 1001 is a 2 by 2 identity matrix, while the matrix denoted by I3 equals to 100, 010, 001 is a 3 by 3 identity matrix. Upper triangular matrix. A square matrix denoted by U equal to in bracket Uij is called an upper triangular matrix if all the elements below the leading diagonal are zeros. This is an example of an upper triangular matrix. U equal to 6403. This is the leading diagonal. You can see that the element below this diagonal is 0. So this is a 2 by 2 upper triangular matrix. Also, this matrix U is a 3 by 3 upper triangular matrix. Lower triangular matrix. A square matrix denoted by L equal to in bracket Lij is called a lower triangular matrix if all the elements above the leading diagonal are zeros. This is an example of a lower triangular matrix. L equal to 6043. This is a leading diagonal. The element above it is 0. So this is a 2 by 2 lower triangular matrix. Also, this matrix is a 3 by 3 lower triangular matrix. Zero matrix. A zero matrix is a matrix with all its elements zeros. This is an example of a zero matrix. This is a 2 by 2 zero matrix. This is another example. This is a 3 by 3 zero matrix, and so on. Row and column matrices. A matrix with only one row is called a row matrix. For example, R equals to 4 minus 3, 2, 7 is a 1 by 4 row matrix. That's it has only one row but 4 columns. A matrix with only one column is called a column matrix. This is an example of a column matrix. C equal to 7052. This is a matrix with only one column but 4 rows. So we call this 4 by 1 column matrix. Symmetric matrix. A square matrix is said to be symmetric if the elements symmetric about the leading diagonal are equal. That is, if A transpose is equal to A, then the matrix A is said to be symmetric. Example 5. This is a symmetric matrix. This is a 3 by 3 symmetric matrix. As you can see, this is a leading diagonal. These two elements are symmetric about the leading diagonal. You can see they are equal. This one and this one are symmetric about the leading diagonal. They are equal. These two are also symmetric about the leading diagonal. So this matrix A is a symmetric matrix. Skew symmetric matrix. A square matrix is said to be skew symmetric if the elements symmetric about the leading diagonal are equal but opposite in signs. That is, if A transpose is equal to minus A, the matrix A is said to be skew symmetric. We know that in a skew symmetric matrix, the leading diagonal element are all zeros. Example 6. This is an example of a 3 by 3 skew symmetric matrix. As you can see in this matrix, the leading diagonal elements are all zeros. And the elements symmetric about this leading diagonal are equal but opposite in sign. You can see here we have 3 here but minus 3 here. Here we have minus 2 but 2 here. We have 6 here but minus 6 here. So this is a skew symmetric matrix. Hermitian matrix. A square matrix A with complex element is called Hermitian if it is equal to its conjugate transpose. That is, if the transpose of A conjugate is equal to A, the matrix A is said to be Hermitian. Example 7. Let us consider this matrix A with complex element. These are the complex element: minus 5 plus 3i, minus 5 minus 3i, where I is an imaginary unit. Now let us find the conjugate of this matrix. A conjugate, denoted by A bar, is obtained by changing the sign of the imaginary part of the complex number. Here, plus 3i is the imaginary part of this complex number. So if we change the sign to minus, we'll have minus here. The imaginary part here is minus 3i, so we change the sign to plus 3i. So this matrix is now the conjugate of the matrix A. Let us now transpose this. The transpose of the conjugate of A is now this. Clearly what you have here is the same thing as A. So we have shown that the transpose of the complex conjugate is equal to A. Hence the matrix A here is an Hermitian matrix. Skew Hermitian matrix. A square matrix A with complex element is called skew Hermitian if it is equal to negative of its conjugate transpose. That is, if the transpose of A conjugate is equal to minus A, then the matrix A is said to be skew emission. Example 8. Let us consider this matrix A with complex element, and let us take the conjugate of this A. A conjugate will be, this is the imaginary part, so we change the sign to minus 2i. The imaginary part here is minus 3i, we change the sign to 4 plus 3i. The imaginary part here is minus 3i, we change the sign to minus 4 plus 3i, and then 0. Let us now transpose this. Transposing this, we have transpose of A conjugate equal to, this row is now this column, the second row is now this column. Now let us factor minus sign out. If we bring out minus sign, what we have left here will be 2i. This element will become 4 minus 3i, while this one will become minus 4 minus 3i, and we have 0 here. So what we have here is the same thing as our original matrix A. So we have shown here that the transpose of A conjugate is equal to minus A, which therefore implies that A is a skew emission matrix. Unitary matrix. A square matrix A with complex element is called a unitary matrix if the product of the transpose of A conjugate and A is an identity matrix I. Example 9. Let us show that this matrix A with complex element is unitary. Solution. First, let us take the conjugate of our A. This is the A conjugate. We transpose it and then multiply by A. This is the transpose of A conjugate, then multiplying by A. As we shall see later on how to multiply matrices, we multiply row by columns. So multiplying, we will obtain this. This row times this column will give us 1 all over 2 minus I squared over 2. This row times this column will give us I over 2 minus I over 2. Now this row times this column will give us minus I over 2 plus I over 2. And this row times this column will give us minus I squared over 2 plus 1 all over 2. Please note, as we shall see when we are going to consider complex number, that I squared is defined to be minus 1. So minus 1 over 2 will become plus 1 over 2. So half plus 1 over 2 is 1. I over 2 minus I over 2 is 0. Minus I over 2 plus I over 2 is 0. Here I squared is minus 1. So minus 1 over 2 is plus 1 over 2, plus 1 over 2 will give us 1. So we have shown that the transpose of A conjugate times A is an identity matrix. Hence, the matrix A is a unitary matrix. Orthogonal matrix. A square matrix A with real element is called an orthogonal matrix if A transpose A is equal to I. We know that the determinant, as we shall see later, of an orthogonal matrix is either plus 1 or minus 1. An orthogonal matrix whose determinant is plus 1 is said to be proper, while the orthogonal matrix whose determinant is minus 1 is said to be improper. Example 10. Show that the matrix A with element cos theta sin theta minus sin theta cos theta is an orthogonal matrix. Solution. First, we transpose the matrix A and then multiply it by A. The transpose of A is this. This row is now this column. This row is now this column. Then we multiply by A. This is the result. Row 1 times column 1 will give us cos square theta plus sin square theta. Row 1 times column 2 will give us cos theta sin theta minus sin theta cos theta. Row 2 times column 1 is sin theta cos theta minus cos theta sin theta. Row 2 times column 2 is sin square theta plus cos square theta. We shall see shortly that cos square theta plus sin square theta is equal to 1. So this will then give us 1, 0, 0, 1. We have shown that A transpose A is equal to identity matrix. Hence, the matrix A is an orthogonal matrix. Thank you for watching. Keep on watching.